Okay, section 5.3, I'm excited. We're finally doing the simplex algorithm, one of the greatest algorithms of the century, invented by George Danzig. And so here we go. Simplex algorithm. We've talked a little bit about the setup here. We're going to start with a basic feasible solution, which we know is an extreme point of our feasible region. And we want to move to an improving basic feasible solution until we converge or we've shown that the problem is unbounded. Okay, so we're going to start with a small example. We'll see, we'll do several iterations of the simplex algorithm on this one here. So just two variables, x1, x2, non-negative, all linear, ax less than or equal to b. So we have some bound constraints, x1 and x2 are between 0 and either 3 or 4, and a linear main constraint. If you put that in standard form, we can actually display this in a table form. There's other forms that are possible. In fact, section 5.4 goes into some other alternatives, but we're going to use this semester. And maybe before we do that, let's go ahead and, because it's in two-dimensional space, we could graph the feasible region and the contours. So let's do that over here. X1, x2, x1 is between 0 and 3. x2 is between 0 and 4. So we actually just start with the rectangle. The bound constraints give us that. We're in that region. And then we have this one inequality. We'll treat it as equality first. It's a line. Equality is a line. So I'm just going to pick a couple points. Let's see. When x is 3, when x1 is 3, x2 is what, 9, 4.5, so 3, 4.5, so it'd be about here. And when x is 4, x1 is 4, 12, 6, 3. So we're at this point, and it actually looks like then that constraint, that main constraint, we're less than or equal to that. So we're on this side, we pick 0, 0 satisfies it, yeah. So we'd be here, here, here. And this ends up being a redundant constraint, right? So really we're just, this rectangle is the feasible region, everything there. And then we put our contours for the objective function. So we're graphing something like, let's see, 4x2 equals minus 2x1 plus some constant for different values of k, divide by 4. So x2 is minus 1/2 x1 plus constant. So I just need to graph this minus 1/2. So it'd be things like this. And clearly we would leave the feasible region. This would be our x star. Okay, so let's then, now that we've got the feasible region, the optimal solution, the contours on there, let's actually go ahead and put this in standard form so you can see where this table comes from. So let me make some space here. Let's see, so we just need three artificial variables that all happen to be slacks. So we need a plus x3 equals 18, a plus x4 equals 4, and a plus x5 equals 3. And then thered be a 0x3 plus a 0x4 plus a 0x5. x1 through x5 greater than or equal to 0. Okay, so standard form, and then we're just going to pull off. It's nice to see once it's in this table. This is actually very easy to enter into MATLAB then, right? Because you've got your objective coefficients, your A matrix, your right-hand side B. And so the only part that's new for us now is labeling these 5 variables. So 5 of the variables, if you are non-basic, you get a value of 0. If you're basic, you solve the system and figure out what the value is. And so last section, he kept proposing sets of variables to be basic and non-basic. And this time we're going to do that. So suppose out of the air someone gifted you that, hey, why don't you make x3, x4, x5 basic and see what your basic solution is. First of all, is that a basis? Does the A matrix, by pulling off that submatrix, that 3x3 matrix, is that a basis? Okay, well, that's really easy to see because the identity matrix spans all of R3. So check, it's a basic solution. And you get the solution by solving. This is a really easy system to solve then. So our basic variables take on 18, 4, and 3. Is that a basic feasible solution? How do you check that? Are all of these values non-negative? Yes. So actually our basic solution is a basic feasible solution. And so we're going to call that x0. That's our initial basic feasible solution. It was obtained by picking a certain set of variables to be basic. They uniquely solve the remaining subsystem. And then what's left over are your non-basics, and those are forced to be 0. Okay, so again, getting this may be hard, and we're going to start off with ones where it's very easy, like this sort of problem, ax less than an e. If you have ax less or equal to b problems in general, it's pretty easy or very easy to get your basis. Just take all your slacks, because remember, you're going to have to add in a bunch of plus y, and all those y's are your slacks. Make those your basics to start. But for other problems, it's hard to do that if it's not in general like that, and then you do the two-phase or the big M. We'll get to that. So in 5.3 though, we're going to start off with either being given an initial basic feasible solution or being able to obtain one very easily just by inspection. Okay, so then let's actually go back to the graph though and think about this basic feasible solution occurred when our original variables were 0, 0. So here is where we are. This is x0. Okay, now the next step in the algorithm though, simplex is a special case of that general improving search algorithm. And the next step is we need a direction vector. Okay, good. You're at an initial feasible solution. For us, a basic feasible solution, which means we are on, in three-dimensional space, we'd be on an extreme point. An extreme point. But we want to do these three things in the simplex. Improving search, yes, you wanted to maintain feasibility. Yes, you wanted to improve the objective. And this is what's added in the simplex. We also want to make sure that direction vector gets us to another basic feasible solution. So one extra condition for the simplex, but that's actually what makes the simplex magic work. Okay, so here's our goal is to get this delta x that does these three things. But let's think about these questions before we start doing the iterations, the simplex iterations. So geometrically or graphically, in what direction should this delta x be? We talked about this in the last couple sections. Again, in our three-dimensional example, if we're at this extreme point here, we want to move along an edge because we are in a convex feasible region and we want to stay on the exterior. And so in our picture here, we're in R2 problem, we want to move along the edge. Well, there's only two ways to move, here or here. Right, so again, we want to move along an edge. And so the next question, given that we're at this basic feasible solution x0, how do we find an adjacent basic feasible solution? We move along one of our edges, but how do we do that? So that is visually, but how do we talk about adjacency in terms of a definition or how it related to our set? Our active constraint set was the set of constraints that were tight or binding or satisfied as equality at the solution that you're at. And now we want to get to a new BFS. So we're at x0. We want to get to x1, where x1 only has one difference in its active constraint set with the active constraint set of x0. So again, here's x0, here's x1. They each have a list of active constraints associated with them. And in that list, they can only have one difference. If that's the case, then that guarantees that x0 and x1 are adjacent. Okay, so we're going to look at our active constraint set to do this. Okay, but for the simplex, because it's an extreme point algorithm, what are your active constraints at the basic feasible solution? Let's think about it. Once we put our problem in standard form, this represents AX equal B. Those are all equalities. And so you just have to go down here and look at this row. Don't forget your simple constraints. Your simple constraints were that all of these xi's are greater than or equal to 0. So the only things you have to check is look here. It'll always be basic feasible, so these will always be non-zero. So anything here that's 0, those correspond to your active constraint set. Because we're looking at an extreme point method, right? Because we're doing the simplex. So any non-negativity constraints that are equal to 0. We don't even have to check the main constraints because we have forced them to be equality and active in that case. All right, we're going to erase the board and we're going to actually get our delta x then. Okay, so we're going to talk about these red lines here and how we got them. These are going to be our direction vectors, and actually at x0 we have 2 different direction vectors that we can move in. There's only 2 choices, and here's how that came about. The simplex directions delta x are constructed by increasing one non-basic variable, leaving the other non-basics unchanged, and computing a unique corresponding change in the basic variables that maintains equality. And that happens if a delta x equals 0. So remember, we want ax equal b. And there was a box back in chapter 3, box 3.25, that said that happens as long as your direction vector satisfies this condition, a delta x equals 0. So go pause the video, go back and review that in your notes or in the chapter. That's on page 118 is what this box is. So that was the conditions that a delta x would be feasible if that is satisfied. And so we know this is the case. And another conclusion from this statement here is that there will be a simplex direction delta x for every non-basic variable that we have. Well, in this problem, there are 2 non-basics. So we're going to have a delta x for x1 and a delta x for x2. We can compute both of those, and we will, and we'll see which one is improving or most improving, right? We need it to be an improving direction. So by this statement here, if we construct a delta x in this manner by solving this linear equation, we know it'll be feasible. Then we have to check, is it improving? And we also know by doing it this way that we'll be moving along an edge, and therefore if we set our lambda just right, we'll actually get to another basic feasible solution. So we will have satisfied our 3 conditions. All right, well, the first condition is that it maintains feasibility. And again, that comes from this key right here. Okay, so for delta x associated with the first non-basic variable of x1, what you do is you let x1 change. It was basic, it was non-basic, it was at 0. So if you increase it just a little bit, it'll become basic. And so you're going to increase it. You leave the other non-basics unchanged, so you keep those 0 for any other non-basic. And then you're going to try to solve for the other changes. And so that would be the x3, x4, x5 components. So we want to solve this linear system here. It's a is 3 by 5. This delta x vector, we have forced some of the components, and then there's 3 that remain we have to solve for. So it's a 5 by 1 vector, but we know 2 of the components. And therefore, we have a 3 by 1 right-hand side for this system right here. Okay, so if you solve this, go ahead and pause the video and do it by hand for this problem. Here's our A. Go ahead and solve your delta x3, your delta x4, your delta x5, and you'll see that delta x3 is -3, delta x4 is -1, and delta x5 is 0. Easy to do by hand on this problem, but you can also, MATLAB loves to solve linear systems. So just go ahead and you can do the / command. You enter this is your A, this is your B, and you do like call a vector delta x is A / B. And it'll spit out the delta x. Okay. But let's think about this. So let's think about this vector here. We're actually in 5-dimensional space on the standard form problem once we've added our auxiliary variables. So we're at some point we're in higher dimensional space. We really can't visualize it. But if we go back to the original space, the original problem only had 2 variables, x1 and x2. So this was our feasible region. Well, let's think about what our change vectors look like. The change vector says go 1 in the x direction, 0 in the y. So it's this vector here. That is our delta x for x1. And this is our delta x for x2. That makes sense. Like we have forced it to go along the edge. And again, in more complicated, higher dimensional problems, that absolutely holds. You will be following an edge of the feasible region. At this point, x0, there are 2 edges leaving. There are 2 non-basic variables. There are 2 direction vectors that we can get. All right, so you do the same thing for this next row. You'd solve a system. Well, let's make some space for x2 now. Same A, except delta x becomes 0, 1. Now you're solving this system. So go ahead and put in A, write it out by hand, and you will solve for a delta x3, delta x4, delta x5, and get these components here. Okay, so we have, again, let's review. We have formed a delta x. There's 2 of them. There's one for every non-basic variable. We happen to form them. We listed all of them. For a bigger problem, you might have 15 delta x's you could get because there's 15 edges leaving from that point in higher dimensional space. Well, you just need one that's improving. So again, we've sort of exhaustively done it here just to demonstrate, but you just need one that's improving. We know both of these satisfy feasibility. Move in those directions and you're still going to be feasible. We need to know which one's improving. May or may not be improving. I think it's going to turn out for this one that they are both improving, right? So I'm starting at a level curve objective function value of 0. And so I go this direction and I'll improve and I'll improve. So both of these should be improving and we'll see that in a minute. So these 2 directions maintain feasibility. It looks like they're both going to be improving. We'll check that algebraically. And then the third thing we need to know, how far do we go? What's the lambda? How far to go in any of the improving directions to be sure that when I'm done, I'm at a basic feasible solution. So I want to know, I want to get here or here, depending on which delta x I've chosen. Okay, so let's erase the board, make some space. Okay, so we have a hunch that either of these directions, we've got 2 directions, one for every non-basic, there's 2 non-basics. We think every one of those, both of them should give us improvement. Let's check that. Remember, for a maximization problem, if you dot your gradient with your direction vector and it's positive, you are improving. We're going to have a special case because we are a linear program. We just have to check C. So if C dotted with the direction vector is greater than 0, we have improvement. We do this so often in linear programming that we actually give it its own notation and a name. It's called a reduced cost. CJ bar is a reduced cost, and you're going to compute that for every non-basic variable J. So we'll have a CJ for every non-basic. And so for our example over here, we had 2 direction vectors for the 2 non-basic variables, so we can get a C1 bar and a C2 bar. And I just put them over here, and you get it by just dotting C right here with the direction vector. And so we get 2 plus 0 plus 0 plus 0 plus 0 is 2. And then we take the next direction vector. It's a candidate direction vector. We hope it's improving. We dot it with the objective function. We get 0, 4, 0, 0, 0, so 4. They're both improving, so check. We can use either. And there's different strategies, different industrial codes. Sometimes some say, hey, do a greedy approach. Take the one that gives the most improvement. Of all the ones, some of them say, just take the first one. It doesn't even matter. I don't need to compute all of them for every non-basic, because again, remember that scenario I just had, suppose there were 15, suppose there were 1,000 different non-basics that I could choose. Easily happens for these airline industry problems or Amazon. If that's the case, don't compute all 1,000, just compute any one that's improving, or maybe 5 and take the most out of that. So there's different strategies. If you're coding this and working for a company, they'll all eventually get to the same place. Sometimes there's little speed ups, little micro improvements. So again, it doesn't matter, but now our next question. Okay, so we have guaranteed that these delta x's maintain feasibility because we solved a delta x equals 0, box 3.5 guaranteed us that. We've now checked of those which are improving. And that's a simple thing to do by just checking is the objective function dotted with the change vector greater than 0 for a max, less than 0 for a min. For ours, it turned out both of them were improving. Okay, so maintain feasibility, improving. Next one, you want to get to a basic feasible solution. And we're showing that has to be adjacent because we're following an edge. So really that is a question about lambda. What is the step size? So I'm at a point, riding along an edge, a vector, and I want to know how far do I go so that I don't leave the feasible region and I'm just barely on the edge of that, then I know I'm actually at another extreme point. So we're trying to get our lambda. All right, so we'll make some more space and we'll figure out how to do that. Okay, to get our lambda, here's our key idea. We're going to take the biggest step size we can that preserves feasibility, because we want to, if we're here, and let's say we're following this direction, the x2 one, the change vector for x2, so we're going to go up this direction. We want to take the biggest step size we can that preserves feasibility. We don't want to stop here or here, and we certainly don't want to go past. We want to take the maximum lambda that we can that still makes us feasible, and that would get us to this point. So we'd like to maybe, if this is the direction we're going to choose, either one would work, but if this is direction, this is what we want to be our x1. Right there. And so we need to know what's the lambda that's going to do that for us. But let's take a look. We're gonna do something called a minimum ratio test, and let's figure out where that came from. First thing, if we want to preserve feasibility, are there any restrictions on the lambda with respect to the ax equal b constraints? This part here. Are there any restrictions on that? Well, again, that was already by design, our delta x satisfies that. The only thing we're worried about are the non-negativity constraints. Some of those could be active, and therefore those are the ones we have to worry about, making sure we maintain feasibility. And so what happens with the minimum ratio test is we look at any components in our change vector that are negative. Right, here's our initial basic feasible solution. Satisfies our ax equal b, satisfies our non-negativity. By design, has to be the case. So all of these are non-negative. But if there's any change directions that are negative, there's a chance I could make the lambda go too far and again be outside the feasible region. So this component doesn't bother me. This one does, this one does. And then same thing for the other change vector for the x2. For looking at this row here, I'm only concerned about negative values in this direction vector, because then I could go past, I could make this, I'm at 18 now. If I made lambda 10, I'd go 18 minus 2 times 10, so 18 minus 20, I'd go minus 2, and I would no longer satisfy the non-negativity constraint. Okay, so that's where this minimum ratio test comes from. It says only worry about the ones, the delta xj's that are negative. So that let's, again, make up our mind that we're just gonna, let's say we're just focused on this one, because maybe we're greedy and we said they both improve, but this one has the most initial local improvement. So let's go with that one. In that one, there are only 2 components that concern us. Those are the delta x3 component and the delta x5 component. Those are the 2 that are negative. And all I have to do is choose the minimum of, in this example, x3 started at 18 and x5 started at 3. And so I need to choose the minimum of negate the negative, so negative, this actually becomes a positive, negative, that becomes a positive. So 9 and 3. The minimum of 9 and 3 is 3. So I'm going to set my lambda to 3. You can compute a lambda for each delta x. Again, it makes sense though, especially doing them by hand, but even doing them with computers, because you will be coding the simplex algorithm with your team. It makes sense just to pick one. Lots of choices for doing that: greedy, random, first one that is improving. Okay, so I picked one, and here's a lambda associated with it. There will be one and only one lambda associated with that. Now, if we do that, let's get to our next iterate then. So let's make a little space here, add one more line to this table, and let's get to x1. How do you get x1? Remember, it's just x0 plus lambda times delta x. And we've set some things here. We force lambda to be 3, and we're using the delta x in the green right above us. Okay, so I need to take 3 times this row in green and add it to this row right here. Okay, so 0 plus 3 times 0 is 0. 0 plus 3 times 1 is 3. 18 plus 3 times minus 2 is 18, minus 6 is 12. 4 plus 0, 4. 3 plus 3 times minus 1, so 3 minus 3 is 0. So here's our next iterate. Notice with this next iterate, it's feasible by design. The non-negativity constraints are satisfied by design. Ax equals b. You can check that, plug this in. Ax equal b, it will hold. Non-negativity is satisfied. And we have now non-basic, basic, 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 non-basic variables. And just to use our, you'll see this language a lot, that we say variable x2 enters the basis, right? X2 was non-basic and then it entered the basis. And we say that x5 left the basis. So this was an x2 enters the basis and x5 exits the basis. So our basic set started out at 3, 4, and 5, x3, 4, and 5, and it became x2, x3, x4. And therefore the basic columns started out as this. And then they became this. What? Has to be a basis. Easy to check the first one, that identity was a basis, but this also is a basis. Do a little RREF form and you'll see that it is full rank. Okay, so then let's go to algorithm 5A. Okay, so in your book, this is page 235, 236, algorithm 5A, simple simplex search for linear programs. Okay, and this is what you guys are going to code with your team in MATLAB. You're going to get good at doing these by hand, so you can check every step of your MATLAB. There's a few small examples you have to demonstrate it on, and you also have some practice problems at the end of this section to do by hand. So you'll have plenty of practice, and once you've coded this, you know the simplex intimately, and you'll have no problem. Okay, so you start with an initial basic feasible solution. Again, sometimes that's hard. Sometimes it's gifted to you. In this MATLAB program, it's basically gifted because I'm giving you AX less than or equal to B problems, which means it's very easy to get an initial starting feasible solution, just like we did here, right? You're always going to have some identity hidden in there in the beginning. Okay, then simplex directions, you're going to construct your simplex direction. For every non-basic, you can compute one, compute You don't have to compute them all, just until you get one that is improving, you check improvement with the reduced cost, which is simply taking the gradient of your function, which is really just the c vector because we have a linear function, with your delta x. Now remember, in step one, your delta x is obtained by using box 3.5 and solving a delta x equals 0. So you're solving that linear system. Again, MATLAB's good at doing that. You want to probably massage it a little bit, because remember, you're fixing some things. Like we had fixed, and we had a delta x equals 0, and there was a 1 and a 0. So we actually, instead of having 5 things to solve for, we only had 3. So you'll do a little massaging to get to that. Okay, optimality. If no simplex direction is improving, that means you had no reduced costs for maximization that were greater than 0. That actually means the problem, you can terminate. There's no, you've moved from one iteration to the next and there's nowhere else to go. That's the best. But there's also the case, I think we forgot to talk about that in step 3. Once you've got your initial basic feasible solution, you've got a direction. How far do you go? That's step 3. Your step size, you just do the minimum ratio test. Only for the components in your change vector that are negative. Those are the only ones that might potentially, if lambda is too big, violate feasibility. And so you're going to check this, choose the minimum. But what if there is no negative component in your delta x? We had 2 in each of ours. What if if your delta x was all non-negative? It actually means that you could go as far as you wanted. There was no min ratio test, nothing where you violated. So you could actually set lambda to infinity, and that means the problem's unbounded. So you can check that. In this case, all of your problems are going to be nice. Your example ones for the MATLAB will be nice. And then here's our standard improving search iterate that we do over and over. And you can just do them quickly in your head, or have MATLAB coded, but it'll be nice to make these tables and go on. So once we get to x1, we'd make another. We take every non-basic. Let's go ahead and stop share for a moment. We take every non-basic. There's 2 this time. We'd form a delta x for x1. We'd form a delta x for x5. We'd have 2 more rows with those delta x's. We check, are those delta x's improving by getting a reduced cost. So we have a C1 bar and a C5 bar. Take whichever one is improving, any one that's improving, and then you're going to form your step size lambda by doing the minimum ratio test. So you'll have a couple more rows, and you'll just continue on making these rows until you get to there's no improvement. And that would be when your CJ bars, there's no CJ bar that is positive. So you can stop, there's nowhere better. In this case, if you were to, and this is good to practice for homework, finish this, do one more iteration, you should go from here, following this edge, you would get to x1. Oh, in fact, we did, right? And then you should go here. Okay, check that out. And then here's some other problems to practice that'll help you get ready for your quiz and for MATLAB's 5A. So algorithm 5A, that's the key one. You're going to know that very well on page 235. And problems from chapter 5 are numbers 6, 7, 9, 12, 15, and 18. They're not full simplex on problems. They'll put you as usual at parts of the problem, and you do a few steps of algorithm 5A. You'll get more and more familiar with it. So my picture was off, and maybe you caught this earlier. Hopefully didn't confuse you too much. But my drawing, I had the rectangle this way. For some reason, I just in my head flip up the x1 and x2, their bounds. So the x1 was less than or equal to 4, and the x2 is less than or equal to 3. And we do have this redundant constraint here, that main constraint. So everything else looks similar. We started at x0, 0, 0. We did our, we had 2 direction vectors. We chose to go in this one, which was the delta x for x2. We got our lambda was 3, and that got us to the next iterate, x1 was 0, 3. And so I had gone to 0. I had 0, 4 in the picture before, but it didn't make sense with what we had in our table over here. And again, now it does because my picture is correct. And if you do one more iteration of the simplex algorithm, get your direction vector. In this case, there are 2 direction vectors. There's the one going this way, and the one going this way. Clearly, this one is improving from our picture, right? Because these are objective function contours in moving direction maximization, and this would be actually going back. And so you will check, you'll see that this direction vector is non-improving. Don't choose it. There's only one that you could choose. It's this one. You'll choose it. You'll get your minimum ratio test, and you'll see that lambda is 4, and that'll send you right here to the next basic feasible solution. It sends you as far as you possibly can without leaving the feasible region. It turns out that at this point then, there are 2 edges that you could follow. You could go back the way you came, that's non-improving, or you could go this way, which is also non-improving. So your CJ bars, your reduced costs, in that case, none of your CJ bars are greater than 0. Therefore, stop the algorithm, you've converged, you're at the optimal solution. It's given by 4.3. All right, so do a few more iterations and check that, and hopefully it all makes more sense now with this correct picture. Okay, sorry about that.